This video is about hydrogen bonding, and I decided to put this video together because I didn't notice there being many examples of hydrogen bonding in the worksheets, and it's a really important intermolecular force, especially in biology, which everybody's going to be taking next year. So I think it's worthwhile spending a little bit extra time, very little extra time. This will be a short video, but I think it'll be useful for you to watch this. Hydrogen bonding is an especially strong dipole-dipole interaction. It's so strong that it qualifies having its own special name, okay? Otherwise, we would just be talking about London dispersion forces and dipole-dipole interactions. But hydrogen bonding is so strong and so special that it's got its own name. One of the reasons it's so special is because it's so important in biology. The reason that DNA works the way that it does in biology is because of hydrogen bonding. The way that proteins work and enzymes work is due to hydrogen bonding. Okay, and I'll leave those details for when you actually take biology. But hydrogen bonding is an intermolecular force that you would see with molecules that have OH, or oxygen, connected to hydrogen, okay, and nitrogen connected to hydrogen, and fluorine connected to hydrogen. Now, in this diagram, I drew a molecule, cartoon molecule, with an OH connected to it, okay? This molecule will experience hydrogen bonding with molecules like itself. This molecule will experience hydrogen bonding with other molecules like itself. It's got a nitrogen connected to a hydrogen. Fluorine connected to hydrogen, this will exhibit hydrogen bonding, but there is no other example with fluorine connected to hydrogen. This is the only way that fluorine and hydrogen can come together. Now, just to clarify what I meant by molecules coming together with other molecules like themselves, for instance here, I've got this molecule with an OH on it, and this molecule, which is different, but it's also got an OH on it. Now, here I actually drew this a little bit more properly. I drew it as a bent structure because that oxygen, just like water has a bent structure, this is going to have a bent structure also because of these lone pair electrons, all right? So this hydrogen is going to be attracted to this negative side, right? Remember, this would be a negatively charged, partial negative charge on this molecule, okay? And here's a molecule with an NH, and here's another molecule similar because it's also got an NH connected to it. And you can see that this lone pair here is attracted to this hydrogen there, okay? And so these are hydrogen bonds. These are examples of hydrogen bonds. I'm going to draw another example. All right, here I'm drawing water, just plain water. I have 5 water molecules. And you can see how these water molecules have oriented themselves, where the positive and negative sides of the water molecules have lined up, okay? All right, so what we're seeing here, this blue dotted line there, and this blue dotted line, and that blue dotted line, and so on, these are all examples of hydrogen bonds, okay? I told you before that water is a remarkable molecule, okay? The reason that I say that is because water is incredibly small for a molecule as far as The molar mass for water is only 18 grams per mole. But the hydrogen bonding between water molecules is incredibly strong. We saw this in class when we looked at our simulation, and we saw that it took a lot of energy to separate water molecules from each other, right? It would take a lot of energy to separate these guys. If you separate them, then you create a gas, right? And it takes a lot of energy to make water separate, okay? It's got a very high boiling point. All right, now I want to show you another molecule that would see hydrogen bonding. It would experience hydrogen bonding between molecules of itself. This is called ethanol, okay? Ethyl alcohol, all right? It's, by the way, it's the OH that makes it an alcohol. And maybe you can see how this looks very much like water, okay? I mean, if I replaced this with another H instead, so it would be HOH, that would be water, right? So we've replaced here, instead of having hydrogen there, now we have 2 carbons and 5 hydrogens. Okay, so I'm going to get rid of this now and show you. I've drawn this in another way right here, where I have an ethanol, but it's drawn in a little bit of a different way. It's a lazier way of drawing it. CH3, CH2, all right, connected to an oxygen, all right? I have 3 ethanol molecules now, and you can see that now they are attracted to each other by hydrogen bonds. So a hydrogen bond would be experienced right there. A hydrogen bond would be experienced right there. Okay. So there, now we're comparing these two. I've got a bunch of waters here, and I've got a bunch of ethyl alcohols here. All right, now, might be interesting to throw this out there right now. Which of these molecules would have a higher boiling point? Okay, I'm going to write that down. So which of these molecules has a higher boiling point? And just by looking at these diagrams, I'm hoping that you can see that for every one methanol, this is ethanol, for every one ethanol, we only have one opportunity for a hydrogen bond, right? There's only one OH set, that can undergo hydrogen bonding. Where with water, we have more than that. For every molecule of water, we have 2 opportunities for hydrogen bonding, okay? So these molecules, these water molecules, are going to hold each other tighter than these ethanol molecules would, okay? So the ethanol is going to have a lower boiling point. Water will have a much higher boiling point than the ethanol. So the answer to that question would be water has the higher boiling point. All right, having shown you that, I want to give you one other thing to think about, okay? We're going to compare 2 molecules and see which one would have the higher or the stronger IMF, okay? Let's give this a try. Okay, so we're looking at these 2 types of molecules. These are both alcohols, by the way. This would be called methanol. You don't have to know that. I'm just saying, as a matter of fact. This is called methanol, and since this has 1, 2, 3, 4 carbons, this would be called butanol. All right, so butanol versus methanol. Which would have the higher boiling point? Okay, so we've got to think about some things here. Hopefully, you would agree with me that they both are going to exhibit hydrogen bonding. Okay, so by the way, both of these would be soluble in water. All right, these OH groups would undergo hydrogen bonding with water. So water would dissolve methanol and water would dissolve butanol. Okay, but anyway, that's not the question here. Which of these would have the higher boiling point? Okay, so they both have hydrogen bonding. What else do they have, though? Remember, all molecules undergo some degree of London dispersion forces. Okay? So all molecules have London dispersion forces. So therefore, let me ask you, which of these would have the higher London dispersion force? I hope that you would agree with me that this molecule would experience more London dispersion force because it has more electrons in this carbon chain. Okay? It has more electrons than this one does, methanol. So you do have hydrogen bonding, but you also have London dispersion forces. And in this molecule, the London dispersion force is higher. So London dispersion force plus hydrogen bonding. This one is going to have the higher boiling point. All right, I think that's enough for now, but I wanted to give you a little bit more background as far as hydrogen bonding. All right.